Hey guys, welcome back. This is Mr. Lee, just recording a quick video lesson on section 2.2, the second half of 2.2. So in the beginning of 2.2, we introduced everyone to the family of normal distributions, the normal curve. And we said that the normal curve is just a bell-shaped curve. It is unimodal and perfectly symmetric. And in general, the normal curve, no matter whether it's kind of tall and very narrow, or shorter and very wide, with a much wider spread or a very narrow spread. In general, when we're talking about a normal curve, it has parameters of the mean and the standard deviation. The mean is the capital Greek letter mu, and the standard deviation is the lowercase Greek letter sigma. So why is it now mu and sigma instead of x bar and sx? Well, mu and sigma technically are not just mean and standard deviation, they're actually population mean, mu, and population standard deviation. So when you're using a mathematical model or a statistical model like the normal curve, what you're doing is you're using a model, something that represents the actual data but is not the actual data. So this is an idealized version of whatever the actual data is. So the actual data, if you recall the example we had of the Gary, Indiana students and the ITBS vocabulary scores, the actual data was not, perfectly symmetric. In fact, is it in the next slide here? It might have been in a previous slide. But the actual data, the raw data, the real observations, they're not perfectly symmetric. But when we're using a normal curve, we're basically saying that this is a representation of or an approximation of the actual data. And in this statistical model, because it's a model, we basically have the entire population. We don't just have a sample. So that is why what we're using is we want to differentiate this mu from the sample mean and the sample standard deviation. So we use population mean and standard deviation when we're applying the economic or the statistical model. Okay, so the normal distribution, it is obviously unimodal and perfectly symmetric. The parameters of it are right here. Capital N means it is a normal curve. And then the parameters are mean and standard deviation, mu and sigma. Remember that I told you what specific cases normal distribution, normal curves are a good approximation for. I think I gave you 3 different examples, sort of biological characteristics or biological functions, and then standardized test scores like the SAT or ACT, and then finally things that are like automated by machines, like a conveyor belt that fills up, soda cans. Okay, and kind of the last big thing that we learned was what's called the empirical rule. Now, this is not a law. This is not 100% accurate, but again, it's like a model of the model, right? We're modeling something from this normal curve model. And what we're modeling is this empirical rule right here. We're saying if you have this normal curve, and now it's a density curve, so now what we're interested in is not just the curve itself, but really the area that lies underneath the curve. We know that the 2 characteristics of a density curve are that it never touches the x-axis, and that the total area below the curve is 1. So with the 68, 95, 99.7 empirical rule, we said that if you go out from the mean of this thing, if you go out 1 standard deviation and you go to -1 standard deviation. So this area under the curve of this really light green bullet shape is 68% of all of the area underneath the curve. And remember that we said that this is also likened to the laws of probability theory, right? So if you think of one way of thinking of this density curve is that 100% of the data lies inside this area, okay, or under the curve. Another way to think of that is that the probability, the total probability of all the events, all the outcomes underneath this curve is 1. Okay, and so one way to interpret this 68% is that from 1 standard deviation to -1 standard deviations, if I were to randomly select one point anywhere inside this curve, okay, the probability would be 0.68 that that point would come within this interval from -1 standard deviations to 1 standard deviation. Okay, and then percentage-wise, another way to think of that or interpret that is if 100% of the data is underneath this curve, well, 68% of the area or 68% of the observations lie within the interval of -1 to 1 standard deviation. And then from -2 to 2, that is 95, okay, percent. And then from -3 to 3, that's almost all the data. It's 99.7% of the data. And so remember that because this thing is perfectly symmetric, well, you can easily calculate how much are in these tails, right? So below, in this little tail, this tiny little sliver of a tail below -3 standard deviations, well, how much is there? Well, there's 0.3, but that's divided by 2 tails, right? So 0.3 divided by 2, so 0.15. Okay, that's where we pretty much ended off, okay? And then now what we're going to do is we're going to go to calculations. Okay, so the distribution of Iowa test, the ITBS vocabulary scores for 7th grade students in Gary, Indiana is close to normal. It's not perfectly normal, but the normal model is a good kind of approximation for those actual results. So suppose the distribution is normal, okay, capital N means normal, with a mean of 6.84 and a standard deviation of 1.55. So the first thing is let's sketch, okay, and yay, we love sketching these things. Okay, it's a sketch, so it doesn't have to be perfect, okay. So there's my x-axis. Okay, and there is my density curve. Okay, so there's my mean. Now I'm going to go out 1, 2, 3 sigma, 1, 2, 3, -1, -2, -3 sigma. Okay, so I'm going to go ahead and write that this is normal and that my parameters are 6.84, comma, 1.55. Okay, now this is my mean, my mu, that's sigma, 2 sigma, 3 sigma, that's negative sigma, -2 sigma, -3 sigma. Okay, so that's in general what these intervals are. But now we can fill in specific values because we know what mu and sigma are. So mu is 6.84, and we don't know what the units are. Points, I guess. It's a test score, so points. And then we're just going to go, I'm going to go out to the right, then I'll go out to the left. So let's go ahead and clear that. So 6.84 plus 1.55 equals 8.39. So that's the actual value that is 1 standard deviation greater than the mean for these 974 7th grade scores. plus 1.55. So now that's 9.94. Okay. Hogan, what are you doing? Sorry, that's my dog tearing apart some clothes. Okay, and on the other side, so 6.84 minus 1.55. So that's 5.29 minus 1.55. So 3.74 minus 1.55. That is 2.19. Okay, now if these had units, if these were like, I don't know, whatever, I mean, it is quantitative data, so they do have units. Normally I would put the units in there. I just don't know what the units are. And you could also like title this graph like ITBS vocab scores. You could put, for 7th grade students in Gary, Indiana. I actually drove through Gary, Indiana once. It's the only thing I remember is that it's pretty smelly there. Lots of factories. Of course, this was many years ago, but okay. And then down here, how are we going to label this? I don't, this is just scores, but points. Okay. Vocab score. Okay, so there we have part A. Part B, what percent of ITBS? So now the fun part, what percent of ITBS vocabulary scores are less than 3.74? So, well, where is that? So what you would do to solve this problem is you would sketch the model, the actual normal model that we're using, okay, which has these parameters with those values. Then you would actually shade the region of interest. Okay, so to shade the region of interest, what you would do is, okay, so this is what we're interested in is from here, and it says less than. So what would that be, the right side or the left side? Well, it would be the left side, the left tail, right? So it's saying, well, what is the percent of data that's below that? Now, you can do a calculation, okay, on your calculator, which I'm going to show you, or you could just use the 6895. You could, at this point, we really haven't taught you how to use the calculator to do the actual calculation. So let's just estimate using the empirical rule, 68, 95, 99.7 rule. So we know that from -2 to 2 standard deviations, we know that this interval here captures 95% of the data, right? Because that's the second. So that's 68, 95, 99.7. So if that's 95% of all the data, there's 5% in this high tail and this low tail. Well, this low tail is, half of 5% because it's so symmetrical, right? So part B is just going to be, well, 2.5%. And you would write out a sentence, okay? I'm not going to do that, but you would write out the sentence to answer the question in context, okay? You'd say 2.5% of ITBS vocabulary scores are less than 3.74. You could actually just, copy, and I had a student who did this once. She copied word for word the question stem and then just put it and turned it into the answer. And I just thought that was brilliant. Okay, part C, what percent of the scores are between 5.29 and 9.94? So 5.29 is here, and 994 is here, okay? Well, we know that from -1 to 1, we know that that's 68%, right? We know that that is 68%. And let's just label each interval. So this little sliver here, it's 68 divided by 2, that's 34. Whoops. That is 34%, and that is, of course, also 34%. We know that -2 to 2 is 95. So what is 95 minus 68? 95 minus 68 equals, okay, divided by 2. Well, that's about 13.5. Okay, and how did I get 13.5? Because from negative 2 to 2 is 95, right? And then from negative 1 to 1 is 68. So 95 minus 68, okay, on my calculator right there is 27. But I have 2 slivers that have the same area, so just divided by 2. All right, so then let's just finish this off. I know we don't have to, but how much is in this last little sliver? Well, that's 99.7. So 99.7 minus 95 is equal to 1.7, and that divided by 2 is, well, 0.85. Okay, so that is the proportions of the different intervals within the normal distribution, okay, broken down by interval. Okay, but this is all based on the empirical rule. So these actually are not, like I said when I introduced the empirical rule is a rule. It's not accurate. It's not 100% accurate. It's an approximation. Okay. So anyways, let's get back and answer the question. Question C says, what percent of the scores are between 5.29 and 9. So here's 5.29, here's 9.94. So we know that we have 68, and then 68 plus 13.5, right? That's 81.5. So your answer to C would be 81.5% of the scores are between 5.29 and 9.94. Okay. Next slide. So those are using the approximated model, okay, the approximated, the 68, 95, the empirical rule. But now we're going to learn how to actually calculate the actual values of these things on your calculator. Okay, so recall that the standard normal distribution is a normal distribution. Okay, or don't recall. So this is a new thing. So now there's one very special normal distribution, because remember, there's infinitely many normal distributions. It's a family of distributions, but there's one called the standard normal distribution. And how you get the standard normal distribution is, instead of, if you look at this graph of Iowa test of basic skills vocab scores, okay, these are actual scores. Like these, the unit of measurement is points, right? So this is 6.84 points, 8.39 points, 9.94 points on that vocab exam. So if we take the points away and we just standardize all of these, like all the data, if we standardize the entire distribution of ITBS vocab scores, what we would get is a density curve that's also perfectly normal, where everything underneath it is z-scores, okay, because we've now standardized. And remember that the z-score, according to the textbook, according to the test question, according to the authors, z-score is a unitless number. However, I taught you that the z-score is not unitless. The unit of measurement for z is standard deviations. So what you're doing is, when you have an actual normal curve of any type of actual contextualized data, like vocabulary scores on some test, those are these little numbers. But once you standardize all of these numbers, it all just becomes, underneath this curve, it all just becomes 0, 1, 2, 3, and -1, -2, -3. And technically, those are unitless numbers, but in reality, they correspond to standard deviations. So let's go ahead and draw now the standard normal distribution, okay? So, and I'm going to draw it purposely right underneath this, and I'm going to try my best to kind of replicate this. Okay, so it's going to look something like that. All right. And then I'm actually just going to pull this same center down. Well, this center, this mu, this mean was at 6.84. Well, if you standardize all these values, every single one of these infinite number, or these 974 data points, okay, well, what does 6.84 become if you standardize? Well, remember that z is x minus, we said x bar. Now I'm going to say mu, because these are really mu and sigma, right? Because when we're using a model, when we're modeling, we're assuming that we have the entire population, right? Not just a sample, okay? Even though we have a size of 974 observations, now, because this is the normal model, we're assuming that 974 is all there is in the entire population. Okay, so, and we'll talk more about that when we get to chapter 8, and we can talk about what's called the sampling distribution. Okay, but anyways, for now, it's z equals x minus mu over sigma. Okay, well, if you put in 6.84 for x, but mu is also 6.84, you're going to get 0 over 1.55, right? Because 1.55 is your standard deviation. Well, 0 over anything is 0. So this becomes 0. So now in the standard normal, this is 0. Well, what would 8.39 become? What would 9.94 become? What would 11.49? That just becomes 1, 2, and 3. And what would 5.29 become? Well, that becomes negative 1, negative 2, and negative 3. So the standard normal distribution is always the normal distribution that has parameters 0, 1. So now what we're going to use in most of our actual calculations with the calculator, when we're finding out, certain probabilities or certain densities, certain areas between certain intervals, we're going to use the standard normal in our calculator. Okay, that's what our calculator, is set to, is to use the standard normal. Okay. Well, in the standard normal, let's just test your knowledge. How much of the data lies between -2 and 2 standard deviations? Well, it's almost 95%, because, right, 68, 95, 99.7, but let's figure out exactly how much it is. Let's go back to the slideshow. Okay, so one thing you're going to use is what's called the standard normal table. Okay, it's also called Table A. One thing on the AP exam, they want you to know how to use tables. Even though tables are pretty much archaic in this age of technology and software and computing power, they are pretty much, archaic, but they still want you to know how to read a table. Okay. Alrighty. So suppose we want to find the proportion of observations from the standard normal distribution that are less than 0.81. Okay. From the standard normal that are less than 0.81. Well, where the heck is 0.81? Look at my, actually I can do this over here. Where is 0.81? What are they talking about 0.81? Well, 0.81 is the z-score. Okay, because it's probability that z is less than 0.81. Well, these are all z-scores, right? Because we've standardized all that data. So where is 0.81? Well, it's positive 0.81. So it's not over here. It's on the right side of 0. So it's right about, we're just going to approximate, that's about 0.5, 0.75, yeah, something like that. So now let's draw the arrow up, or the line up. And what area? Let's shade the region of interest. Okay, well, what is the probability that z is less than 0.81? So 0.81 is right here, 0.81, and then it's the left tail calculation that we're doing. And it turns out that the calculator always defaults to a left tail calculation. Okay, but before we use the calculator, let's look at the table A. So here's an excerpt from table A right here on the screen. So you simply look at the z-score of 0.8, and not 0.800, but 0.801. or 0.81, okay? And then 0.7910. So what does that tell you? What that tells you is that 79.1% of the data, or of the area below the curve, lies to the left of 0.81. So how you write that in notation is capital P means probability. The probability that little z, okay, our z-score, is less than 0.81 is equal to what? 0.7910. Now, whoops, sorry, that's how you write it. Now, why did I write 0.7910? Why didn't I just write 79%? Because probability, okay, notation-wise, goes with numbers between 0 and 1. Okay, numbers between 0 and 1. You don't talk about probability in terms of percentages. Okay, if somebody does talk about probability in terms of percentages, that is not statistically accurate. Okay, because probability is between 0 and 1. Okay, so let's go ahead and find this on the calculator. All right. So on the calculator, you're just going to look at what's called distributions. So it's up here above vars. So you're going to push second vars, which is basically just distribution. And all these different types of distributions come out. Let me see if I can zoom in a little bit. And all these different types of distributions come in, and you're going to learn a lot of these different distributions. Okay, this is the normal distribution. Number 1, 2, and 3 are normal distributions. Number 4 is the student's t model distribution. 5 and 6 are also the student's t. This is called the chi-square distribution, which is heavily skewed. Chi-square, that's the F distribution. That's the binomial distribution, the Poisson distribution, the geometric distribution. Okay, we're going to do a lot with the normal distribution. Okay, so we have normal PDF, normal CDF, and inverse norm. So inverse norm, you can already tell, you've already learned, inverse functions. So think of inverse norm as an inverse function. Okay, we're going to use it when we want the opposite of what we use inverse CDF for. Okay, inverse PDF, I know the authors maybe teach it a little bit, but we're never going to use inverse PDF. What we're going to use is inverse CDF, the cumulative density function. Okay, that is how you find the area under the curve from one interval to another interval. Okay, so let's go ahead and go to normal CDF. So now it's asking us for the lower bound or the lower interval. Okay, and if you look at what the default is, the calculator default, it's a really low number, right? Because it's -1 times e to the 99th, right? So that's kind of like saying negative infinity, basically, right? Because it's -1 times 10 to the 99th. Okay, so that's a really far left number. The upper bound is, well, what am I going to find? So why would they put negative infinity, more or less negative infinity? Because remember that this curve goes on infinitely without end. So technically, the lower bound is at negative infinity. Okay. What is my upper bound? My upper bound is the highest positive number, and that is 0.81. So 0.81. Okay. Now, mu and sigma are defaulted at 0 and 1. That means I'm just using the standard normal distribution. Okay, standard normal. Now let's just go ahead and paste, enter, and there's my actual value. Notice that the table A, okay, the standard normal table, only gave me 4 digits, 0.7910. The calculator gives me a lot more, 0.7910299747. Okay, so that is how you use the calculator to find the area under the curve from one interval to another interval. Okay, well, let's say we want to find the area under the curve from 1 to, or -1 to 1. Okay, not negative infinity. We want to find this finite interval here, right here. Right? Now remember, the empirical rule told us that that was 68. So see if we get 0.68. Second vars, go ahead and you guys do it. I know you can do this a lot faster than me. So let's just go negative. Now don't do -1. Okay, that's a lesson that you got to learn. Don't use the minus key, use negative. This is the negative key. So type in -1 for your lower bound. 1 is your upper bound, and we're still in the standard normal. So what is it? Quite a bit of rounding error. Okay, the book, the empirical rule says 68. Okay, 0.680. This is 0.68, 2689, 48009. So there's some serious rounding error going on. Well, what about 2 or -2 to 2? Second vars, normal CDF, -2 to 2. Look at that. Huge rounding error. The empirical rule says it's 0.950. Well, 0.954499876. That's a lot of rounding error. Finally, let's go 3 to -3. Second vars, normal CDF. Okay, -3, 3. 0.997. Okay, pretty close. Okay, pretty close. Okay, so that's how you use the calculator. So could you use the calculator? And I used to never teach this until the end because I thought of it as, AP Stats teachers, we kind of look at this as a cheat. But could you use this calculator to find the area under the curve instead of standardizing and then doing a calculation just off the standard normal? Could we just find the calculation off of this? Yes, you can. Okay, but the way we teach calculations with the normal model is we take the raw data, then we standardize this. We do the linear transformation to standardize all the data, and then we use table A, which is the standard normal table. So you have to standardize first and then use table A. Okay, well, the calculator can do all that stuff right there, like in a split second. Okay, but you can actually just use these numbers, okay, because you can change the mu and the sigma, right? So if you know the mu and the sigma, you can actually just put them in here. What the calculator technically is doing, the way it's programmed, is it's standardizing all the data, and then it's just using the standard normal. Okay, but let's go ahead and do that. Let's find the interval of, what is the percent of scorers? That is, let's just choose a number that's not exactly a standard deviation. Let's above 5. Okay, so 5. So where would 5 be? I don't know, somewhere here. Above 5. So, well, let's do finite. So let's go from 5 to, 7. 5 to 7. So what is the percent of data that is in this part right here from 5 to 7? Okay, so let's go second vars, normal CDF. Okay, 5, 7, but now we have to change the mu and sigma. 6.84, 1.55, paste, 42%. Okay, so 42% of the 7th graders scored between 5 and 7, okay, on the vocabulary portion of the ITBS score. Okay, so that is how you use the calculator. Okay, so now how are we going to solve problems? Now this is where you're going to use the 4-step solving process. State, plan, do, conclude. Yes, you literally are going to write out state, plan, do, and conclude. Okay, express the problems in terms of the observed variable x, plan, draw the picture of the distribution, and shade the area of interest under the curve. Do, perform calculations, 2 calculations. You're standardizing first, then you're using table A. And then you're going to write a conclusion. Now, when you have your test on this, on normal distribution calculations, will you get marked off if you do not write state plan do conclude? You betcha. You are going to follow this process of writing state plan do conclude. Okay. Excuse me. All right. When Tiger Woods hits his driver, the distance the ball travels can be described by a normal distribution with mean 304, standard deviation 8. This was from like many years ago. Because now when Tiger hits his driver, his normal distribution parameters are probably about 340 instead of 304. All right. Let's do some calculations. What percent of Tiger's drives travel between 305 and 325? Okay, cool. So now we need some paper. So here's some paper. All right. So state, plan, do, conclude. Okay. State, express the problems in terms of the observed variable x. Okay. We want to know what percent of Tiger's drives travel between 305 and 325 yards. Okay, that's our state. Plan. Draw a picture of the distribution and shade the area of interest under the curve. Okay, so here's plan. Okay, there's state. Plan. We will use a normal model. Here we go. Here's the normal model. Okay. Okay, so we are given 304, 8. So 304 plus 8, 312, 320, 328. Okay, minus 8, 296, minus 8, 288, 280. Okay, let's shade the region of interest. The region of interest is between 305 and 325. So 305 is just right of the mean. Okay, so that's 8, so that's 1/8 right of the mean. And then 325, 320, 8, 1, 2, 3, 4, 5. Okay, so we want to know what is, well, the probability that x, sorry, this should be compound. What's the probability that x is between 304 and 325 yards? Okay, so we can cheat and go straight to the calculator. That's not what the process is, though. Okay, so state plan, do, conclude. So what was do? Let's see, what was do? Do, perform the calculations. Do. Standardize x to restate the problem in terms of a standard normal variable. Now, Mr. Lee, you're wasting our time. Do we really have to standardize? Yes, you do. Okay. If you don't standardize and show your standardization on the AP test, you will lose points. How do you show this standardization? Do I have to redraw this entire curve and center it at 1, 0? Okay, you could, but since I'm an AP reader, I know that the step that you could do instead of redrawing this and putting this 0, 1, 2, 3, -1, -2, -3, and shading the region of interest, okay, all you have to do is figure out these two z-scores. Okay, and we got a little unlucky. A lot of times it's a right tail or a left tail, then you only have to figure out one z-score. But you have to figure out, well, what are these z-scores for 304 and 325? So this is the same as, and this ticks the box, this checks the box for AP readers, the probability, well, what's 305? This is 305, 305 and 320. What is 305 standardized? Well, you can just write this as 305 minus 304 divided by 1/8, or divided by 8, and that's going to be 1/8, right? Because 5 minus 4, okay? And then z, not x, because x is the actual observation. Okay, z is the standardized. So the probability is z 325 minus 304. So that's going to be what, 21 over 8? Okay, so that is the probability that, okay, 1/8, 0.125 z, and then 25 minus 4, 21 divided by 8, 2.65. This again is going to be a pretty large probability, because 2.65, that's almost 3 standard deviations right at the mean, and this is almost at the mean. So this is not going to be quite 50%, but it's going to be a major chunk. And if you look at the diagram, you can see it's a major chunk, right? So it's not 50%, but it's somewhat close. Okay, now we're going to go ahead and use table A. Okay, use table A. Well, I don't have table A with me, so I'm going to go ahead and use technology. Okay, so second vars CDF, okay, 0.125. Okay, this is 2.65. Now we're using the standard normal. We get 0.446237. Now, how many digits should I go to? We're going to go 4 digits. And it is okay on the AP exam, it's okay if you either truncate or round. Truncate means once you go to 4 digits, you just chop everything off and don't even look at it after that, like the 5th digit, none. And rounding means to round. Okay, so look at the 5th digit. So 4462, the 5th digit is 3, so you just leave that as a 2. Okay, so this is approximately 0.4462. Okay, and now you have to conclude, which means you have to write a sentence in context. In context. Okay, it's incredibly important that you use the context. So you have to go back and answer the actual question. Okay, so approximately 44.62% of Tiger's drives travel between 305 and 325 yards. Use the exact language of the question stem. That would get full credit. Okay. Okay, the last thing we have to talk about is completely different topic, somewhat related, but just kind of loosely related. And this is, well, how do we know if the normal model is a good fit? Okay, well, there's mathematical ways, mathematical calculations to figure out how well this normal model actually fits. And you're going to learn the mathematical calculations and the interpretation of those later on. Right now, we're just going to introduce you to a very quick and easy way to just kind of ballpark whether or not the normal model is a good fit for the actual data. And we're going to use what's called a normal probability plot. You guessed it, it's a graph. Okay, so what we're going to do is plot the actual data and examine the plot, and it better look pretty symmetric. It better look pretty bell-shaped. Okay, and then the next thing you want to do is an actual normal probability plot. So look at this plot right here of the actual data. Does that look somewhat normal to you? Do you think the normal model would be a good fit there? No, obviously not. Yes, it's unimodal, but it doesn't look symmetric at all. This is heavily skewed to the right. So when you plot what's called the normal probability plot, this is not going to be linear. This is going to be very curved. Okay, and you can see that it's very curved. Well, how do you know if the normal model is a pretty good fit for the actual data? When you plot the x values against the z-scores, it will be a linear shape. Okay, it will look like a line, not a curve. Okay, if it's curved, strongly curved, it's not normal. Okay, the normal model does not fit. But if it's linear, the normal model is a good fit. I know that this is not a great, like mathematically precise way of assessing normality, but like I said, that's going to come later. Okay, this is just a quick and easy, just visual check. Okay, so is the normal model a good model to model this, to represent this? No, it's not. Okay, so when you're reading a normal probability plot, okay, if the points are close to a straight line, the data are roughly normal. Okay, systematic deviations from a straight line indicate a non-normal distribution. This is systematic, it's linear, right? Math students, you could probably figure out a nice formula for this curve. Okay, outliers appear as points that are far away from the overall pattern of the plot. So you have most of the dots are right here. Then you have a couple dots that are really far away. Those are possible outliers. Okay, and this dot has an x value of 600. That is this thing over here. Okay. So guys, that's all we have right now. Let me just show you where the normal probability plot is on your calculator. So you actually have to have a list of data. Okay, so stat edit. I have, well, this is going to be perfectly, well, this is not a great example of data, but let me just show you where I have some data in my lists from some homework problem from a long time ago. But let's just show you where oops, not alpha, clear. So second stat plot. So my first plot is on, all the rest are off. So let's go to my first plot. And right now it's on a box plot with outliers. So that's not what I want. What I want is the very last graph. This one. My data list is X. My data axis, I want to use X, not Y. Okay, and then let's look at what it looks like. Zoom in. Ooh, very linear, like extremely linear, right? Why would this be so linear? Well, let's look at my data. Stat edit. List 1, 0, 1, 2, 3, 4, 5, 6, 7, or 0, 1, 2, 3, 4, 5, 6. Yeah, that better be pretty linear, right? Okay, but what happens when we do the same thing for list 2? It probably won't look as linear. So second stat plot. Now I want to use L2. Okay, and now let's do a zoom stat. Yeah, not so much, right? It's like a curve. Goes up, flattens out, then goes back up. It's a curve, right? So not a very good fit. Okay, guys, that's all we have time for. Hope you enjoyed the video. Ask questions in the discussion board and enjoy your homework.